Hello everyone, hello person. My name is Gordon Compton and today I would like to introduce you about the topic layer by layer electrolyte membrane containing cerium oxide nanoparticle for proton exchange membrane fuel cell application. And in my topic I have four parts, but the first one I would like to introduce you about the proton exchange membrane fuel cell and how the radical that can generate during the fuel cell application. And as you can see in here, the hydrogen and proton and oxygen that can apply at the anode and cathode side of the fuel cell system, and after that the hydrogen that can transfer to the two hydrogen ion and this can release two electrons, and hydrogen ion that will transfer through the electrolyte membrane to the cathode side, and at the cathode side the hydrogen ion that will react with the oxygen gas to generate the water. And however, during the proton exchange membrane fuel cell application, the radical that can generate from the same in this figure. The first one that is the hydrogen that can transfer to the two hydrogen radical, and hydrogen radical that will make the bonding with the oxygen gas and to represent the H2O2, and the concentration of the H2O2 that will be decreased from the anode side to the cathode side because it's for the oxidized to the water or the radical. And now I would like to talk about the mechanism how the radical that can attack in the polymer structure. As we know that we have two radicals at here, that is the OX radical and the X radical, and the first one that is the attack of the radical in the nephron polymer. We can see the first mechanism that is the attack of OX radical into the carboxylic group and carbonate group at the end of the polymer structure. And another mechanism is very important, that is the attack of the OX radical to the CS and CO bonding, because this mechanism is a very important because it will directly crack the functional group, and that will decrease the potential of the fuel cell system. And another that is the attack of the hydrogen radical in the CF bonding, and this attack that is also very important because this will decrease both the side chain and the main chain of the polymer structure. And different with the nephron structure, the hydrocarbon structure that is containing a lot of ether group at the main chain. So that is the reason the radical that will easily attack to the ether group, and this will be decrease the polymer structure. That is the reason why the hydrocarbon membrane that is also show the low chemical stability. And now I would like to talk about two radical scavengers. The first one that is the metal ion, the second one that is the nanoparticle. As we know, the metal ion that has the excellent radical scavenger. However, the cerium ion that can dissolve in the water, so this will leak out of the membrane during the operation. And the second one that is the cerium ion that can make the cross-linking bonding with the sulfonic acid group, and this acid sulfonic group that will become an activation with the proton, so this will be decrease the proton conductivity of the membrane. And that is the reason in this topic I want to use the nanoparticle. The nanoparticle that will not dissolve in the water, so this will cannot leak out of the membrane. However, the cerium oxide nanoparticle it is the muted conductor, so the cerium oxide nanoparticle can transfer the electron through the membrane. So that is reason in this topic I want to prepare the layer by layer membrane and containing the cerium oxide at both surface layer. And moreover, I also synthesize the SDAES polymer structure and the sulfonic acid group that were grabbed in the side chain of the polymer structure by the sulfide group, and the sulfide group at here that can make the bonding with the radical to generate the sulfone. And sulfone bonding that is very stable in the radical condition. And this is process how I can synthesize the polymer and the cerium oxide nanoparticle. And the first one, I would like to talk about the cerium oxide nanoparticle property. We can see from the DLS spectrum, the nanoparticle size here that is around 5 to 7 nanometer. And the nanoparticle size is very important in this case because it can block the transfer of the proton through the membrane. And this result that is the same behavior with the 10 image in the figure C and D. That's it. Moreover, we can see the cerium oxide nanoparticle that is distribute very well in the solution. And from the figure B, we can confirm the cerium oxide is the crystal spirit. And now I would like to talk about the polymer property structure. And we can see from the figure A that is the main chain of the polymer structure that containing melting group with the bits at 2 ppm, that is the proton of the melting group. And after that I only modify to the sulfonic acid group, and we can see the some bit about 2.5 ppm, that is the proton of the multi-length group in the side chain. And from the figure D, we can see it here that is the signal of the sulfonic acid group, sulfone, and the sulfide bonding. And with the sulfonic acid group in that will at about 168 electron volt, and the signal of the sulfone bonding in the main chain of the polymer structure that is about 166 electron volt, and the sulfide that is around 162 and 163 electron volt. And they are the same image of the layer by layer membrane containing 4% of the cerium oxide. We can see in the figure A that is the electrolyte membrane. This has both the surface layer about 10 micrometer and the middle layer that is around 80 micrometer. And the figure C and D that is the EDS mapping of the cerium and the oxygen element. We can see the region of the cerium element at both the surface layer, and moreover the dark area in the figure D, that is the interface layer between the layer 1 and in between the surface layer and the middle layer. And now I would like to talk another property of the electrolyte membrane, that is the water attack swelling ratio and proton conductivity. We can see from figure A to figure C that is the water attack swelling ratio and proton conductivity of the membrane with different sulfonic acid concentration. When I increase the sulfonic acid concentration from 120 to 160, all the water attack swelling ratio and proton conductivity will be increased. And moreover, from figure D and to figure F, it can show when I add the 2% of the cerium oxide to the two surface layer, that it will not significant effect to the hydration property and proton conductivity of the membranes. And now I would like to talk about another very important property, that is the chemical stability. We can see in the figure A that is the residual weight of the membrane after treatment in the phantom test solution 6 and 12 hours. We can see when I increase the concentration of the sulfonic acid group from 120 to 160%, the residual weight of the membrane that will be decreased. The reason here that is because when I increase the sulfonic acid concentration, that will be increase the water attack and swelling ratio of the membrane. So that is the reason the radical that is easy come inside the membrane and that will be attacked in the polymer structure. However, when I make the layer by layer membrane containing containing cerium oxide at two surface layer, we can see the at the same concentration with the breathing membrane, but it shows the higher the residual weight after treatment, the same time treatment. The reason that here that is because the radical that will be captured by the cerium oxide at the both surface layer, so that will not affect to the polymer structure. And from the figure B, we can see at here that is the OCB tag of the membrane. We can see the recast Nafion membrane and the breathing membrane that will be decayed after about 200 to 250 hours. However, the layer by layer membrane containing 4% of the cerium oxide that's still stable after 500 hours. And figure C and D, that's either sulfonate admission rate of the membrane at the anode and cathode side of the fuel cell system. We can see at here that the sulfonate admission rate of the layer by layer membrane is significantly lower than the Nafion and the breathing membrane. So that's in this result that will be confirmed the degradation degree of the layer by layer membrane that's more better than the another. And it also confirmed the figure E2K, that it also confirmed about the chemical stability of the membrane. We can see the membrane before the breathing membrane before the after treatment 10 hours in the phantom test solution, it will be easy to broken. However, the membrane containing however, the layer by layer membrane that's still stable after treatment. And figure L and N, that's either AFM image of the membrane. We can see a lot of pinhole that appear in the breathing membrane after 10 hours treatment in the phantom test. However, the surface of the membrane containing cerium oxide that's still very good. And the last one, that is I would like to talk about the cell performance. We can see in the figure A that is the performance of the membrane with different of the concentration of the sulfonic acid group, and we can see the membrane containing 160% of the sulfonic acid group. This shows the power density about 150 milliwatts per centimeter squared. Is higher than the Nafion. And figure C and D, that is I want you this result to explain why I want to use the layer by layer membrane. We can see at here that is the layer by layer membrane and the breathing membrane that is so similar power density. However, the membrane containing the same concentration. However, the composite membrane containing the same concentration of the cerium oxide is so very low the power density. And the reason at here that is the same I discussed before. That is because the composite membrane that is containing cerium oxide that can easily transfer the electron through the membrane, so that will be decrease the power density. And the last one, that is the performance of the membrane after I treatment 100 hours by the OCB test. Although before treatment, all of the membrane that is so quite similar behavior. However, after treatment 100 hours, the membrane containing 4% of the cerium oxide is so high with the power density. So that from that result, that can confirm the good chemical stability of the layer by layer membrane. From all the result, I have some conclusion. The first one, that is I already synthesized a study of the SBAES polymer containing different concentration of the sulfonic acid group, and it's so low water attack and swelling rate, but it's so higher than conductivity when we compare with the Nafion. And I already synthesized successful the cerium oxide nanoparticle with the nanoparticle size about 5 to 7 nanometer, and this size that is very important. And when I add about 4% of the cerium oxide into the layer by layer, it will not affect to the proton conductivity of the membrane. And from the and moreover, that is the layer by layer membrane can prevent the electron transfer of the cerium oxide. And finally, we can see the membrane containing 4% of the cerium oxide is so acceptable, so very good. The properties so such as the chemical stability or another. So this has high potential to apply as the proton exchange membrane for fuel cell application. Oh, thank you so much for your listening.
Thank you for your presentation. Is there any question? I have a short question. So, I was curious about the thickness of your membrane without the cerium oxide layer. So, what is the thickness of? I mean, is there any difference between the thickness without the cerium oxide layer?
Yeah. The thickness of the breathing membrane without the serum layer, that is around 80 to 90 micrometer, because I usually the solution casting method, so I cannot handle lower than that thickness.
So I'm asking because I thought that with that cerium oxide additional layer, we would maybe compromise the ionic conductivity, but in your like ivory cup, we don't really see like the decrease of the ohmic, the ion conductivity with your thinner membrane or thicker membrane. So can you go back to page number 11? Next one. The IV cup of your fuel cell performance curve of your,
I understand.
yeah, that one. So the SPAEA 140
Yeah.
shows poor decreased performance than the one with the cerium oxide.
Yeah.
And I thought that the membrane without those additional layer may have better ion conductivity.
Thank you for the question. Actually, in this case, that is the reason I want to synthesize very small the nanoparticle. That is because I want to prevent the effect of the nanoparticle side to conductivity. So, and I already read some paper, and they said that with the small amount of the cerium oxide and with the concentration lower than 5%, that will be not affect too much to the conductivity of the membrane.
Okay. Yeah, but I thought that 20% of increase of thickness maybe not insignificant.
I understand Professor question, and that also that is the increase of the 20% that will quite effect to the conductivity of the membrane. So that is reason in this topic I want to minimize that thickness.
Thank you for your answer.
Thank you.
Any other question? 네, 없으시면 이걸로. Thank you very much for your presentation. Thank you.